The James Webb Telescope is a giant leap in the history of stargazing. With its advanced capabilities, including its ability to peer back in time to the very first galaxies that formed after the Big Bang, the Supreme Observatory is expected to shed light on fundamental questions about the origins and evolution of the cosmos. However, more than 2 years after operation, the telescope, albeit solved a lot of puzzles, is raising big questions about the early universe. The data obtained by James Webb isn't just quite what scientists expected. So, though dazzled by Webb's stunning images of deep space, scientists had to admit that something was amiss. What the telescope has revealed contradicts scientists' current theory of how the universe grew up. And it's beginning to look as if we may need to rewrite the history of the cosmos and reshape humanity's position within it. Join us as we dig deep into how exactly James Webb just broke our universe in 2 years. The James Webb Space Telescope, as you know, is one of the most advanced telescopes ever built. Planning for James Webb began over 25 years ago, and construction efforts spanned over a decade. It was launched into space on December 25, 2021, and within a month arrived at its final destination, 930,000 miles away from Earth. Its location in space allows it a relatively unobstructed view of the universe. The telescope design was a global effort, led by NASA, and intended to push the boundaries of astronomical observation with revolutionary engineering. Its mirror is massive, about 6.5 meters in diameter. That's nearly 3 times the size of the Hubble Space Telescope, which launched in 1990 and is still working today. It's a telescope's mirror that allows it to collect light. Webb's is so big that it can see the faintest and farthest galaxies and stars in the universe. Its state-of-the-art instruments can reveal information about the composition, temperature, and motion of these distant cosmic objects. Thus, for thousands of space scientists, the James Webb Space Telescope is a window to that unknown universe. Just how far back can James Webb peer into the cosmos and into the past? Well, about 13.5 billion years. A telescope does not show stars, galaxies, and exoplanets as they are right now. Instead, astronomers are catching a glimpse of how they were in the past. It takes time for light to travel across space and reach our telescopes. In essence, that means a look into space is also a trip back in time. This is even true for objects that are quite close to us. The light you see from the sun left it about 8 minutes, 20 seconds earlier. That's how long it takes for the sun's light to travel to Earth. You can easily do the math on this. All light, whether sunlight, a flashlight, or a light bulb in your house, travels at almost 300,000 kilometers per second. That's just over 18 million kilometers per minute. The sun is about 150 million kilometers from Earth. That comes out to about 8 minutes, 20 seconds. But the farther away something is, the longer its light takes to reach us. That's why the light we see from Proxima Centauri, the closest star to us aside from our sun, is 4 years old. That is, it's approximately 40 trillion kilometers away from Earth, so that light takes just over 4 years to reach us. Or, as scientists like to say, 4 light years. Most recently, James Webb observed Earendel, one of the farthest stars ever detected. The light that the telescope sees from Earendel is about 12.9 billion years old. The Webb Space Telescope is looking much farther back in time than previously possible with other telescopes, such as the Hubble Space Telescope. For example, although Hubble can see objects 60,000 times fainter than the human eye is able, the Supreme Observatory can see objects almost 9 times fainter than even Hubble can. But is it possible to see back to the beginning of time? The Big Bang is a term used to define the beginning of our universe as we know it. Scientists believe it occurred about 13.8 billion years ago. It is the most widely accepted theory among physicists to explain the history of our universe. The name is a bit misleading, however, because it suggests that some sort of explosion, like fireworks, created the universe. The Big Bang more closely represents the appearance of rapidly expanding space everywhere in the universe. The environment immediately after the Big Bang was similar to a cosmic fog that covered the universe, making it hard for light to travel beyond it. Eventually, galaxies, stars, and planets started to grow. That's why this era in the universe is called the Cosmic Dark Ages. As the universe continued to expand, the cosmic fog began to rise, and light was eventually able to travel freely through space. In fact, a few satellites have observed the light left by the Big Bang, about 380,000 years after it occurred. These telescopes were built to detect the splotchy leftover glow from the Big Bang, whose light can be tracked in the microwave band. However, even 380,000 years after the Big Bang, there were no stars and galaxies. The universe was still a very dark place. The cosmic dark ages wouldn't end until a few 100 million years later, when the first stars and galaxies began to form. The James Webb Space Telescope was not designed to observe as far back as the Big Bang, but instead to see the period when the first objects in the universe began to form and emit light. Before this time period, there is little light for the James Webb Space Telescope to observe, given the conditions of the early universe and the lack of galaxies and stars. Peering back to the time period close to the Big Bang is not simply a matter of having a larger mirror. Astronomers have already done it using other satellites that observe microwave emission from very soon after the Big Bang. So the James Webb Space Telescope observing the universe a few 100 million years after the Big Bang isn't a limitation of the telescope. Rather, that's actually the telescope's mission. It's a reflection of where in the universe we expect the first light from stars and galaxies to emerge. By studying ancient galaxies, scientists hope to understand the unique conditions of the early universe and gain insight into the processes that helped them flourish. That includes the evolution of supermassive black holes, the life cycle of stars, and what exoplanets, worlds beyond our solar system, are made of. However, data obtained by James Webb isn't quite what scientists expected. In the 2024 Isaac Asimov Memorial Debate, astrophysicist and science communicator Neil deGrasse Tyson moderated a discussion at the American Museum of Natural History in New York. The conversation was between scientists and surrounded the topic of how data from the telescope may be shifting our fundamental understanding of our universe. From discrepancies in the age of the universe to the unexpected brightness of early galaxies, the James Webb Space Telescope has already prompted scientists to reconsider how the early universe once operated, leading to revelations that could trigger major shifts in our models of the universe during the next decade or more of James Webb's tenure. And in the words of panelist Mike Boylan Colchin, a theoretical astrophysicist at the University of Texas at Austin, the data from the telescope paints a consistent and consistently new picture of the early universe. The trouble began almost as soon as James Webb first peered into the distant universe. Webb's first views of such distant, ancient regions of space were confusing in two ways. First, some of its images contained huge numbers of galaxies. Far more, in fact, than astronomers thought possible so far back in time. Second, a handful of those galaxies appeared to be monstrously massive. These all dated back to the first 700 million years of the universe. And they were up to 100 times as heavy as scientists thought possible back then. For that reason, these galaxies were dubbed universe breakers. Our current understanding of how the universe grew up goes like this. First, dark matter collapsed into giant clumps known as halos. This happened within the first few 100 million years after the Big Bang. The halo's gravity then pulled in normal matter. This eventually formed stars and galaxies. This would have taken time. Matter would have clumped together slowly, eventually building up larger and larger galaxies. If true, the jumbo galaxies that James Webb spied so soon after the Big Bang shouldn't be possible. What's more, The current story of the universe doesn't predict nearly enough dark matter halos in the early universe as would be needed to build the many big galaxies that the telescope saw. In that light, things look pretty dire for scientists' current theory of how the universe evolved. The case of the surprisingly active early universe might be related to another well-known discrepancy in astrophysics, the age of the universe. The Hubble Space Telescope was a huge factor in helping narrow down the scientific consensus on the universe's age. In fact, the telescope's mirrors were specifically made to observe stars called Cepheids that astronomers can use to calculate that age. The resulting measurement of the universe's age, about 13.7 billion years, has stood ever since. But let's not forget, there is another way to measure the age of the universe. That's with the cosmic microwave background, the light from the earliest phases of the universe. Using this method, scientists came up with a slightly larger number, 13.8 billion years. And while that difference may not seem huge, some estimates using Cepheids are as low as 12.8 billion years. Worse, no one knows where the difference comes from. It's like we're digging a tunnel on opposite sides of a mountain, and we missed. Unfortunately, the surprisingly luminous early galaxies captured by James Webb did nothing to solve this mystery. In fact, the telescope's results led Rajendra Gupta, an astrophysicist at the University of Ottawa, to publish a paper suggesting that, based on the new data, the universe could be as ancient as 26.8 billion years old, about twice as old as current estimates. While the panelists agreed that Gupta's suggestion is extremely unlikely, the discrepancy of the universe's age in general does suggest the standard cosmological model and our understanding of the impact dark matter and dark energy have on our universe may need some revamping. Put simply, it could be that something fundamental is missing in our current picture. What's notable, the impossible early galaxies aren't even the only things that keep cosmologists up at night. The Webb telescope has double-checked the work of its older sibling, the Hubble Space Telescope. Hubble's measurements of the expansion rate of the universe are exemplary, the trailblazing observatory found, further ratcheting up the so-called Hubble tension. Putting it simply, measurements of the expansion rate of the universe, defined by a property called the Hubble constant, just don't add up. On one hand, observations of the cosmic microwave background radiation, which is like a baby picture of the cosmos from just 379,000 years after the Big Bang, say the universe should be expanding today at a rate of about 67.8 kilometers per second per megaparsec. This means that every volume of space a million parsecs across should be expanding at a rate of 67.8 kilometers every second. An alternative way to measure this expansion is by climbing onto the cosmic distance ladder, where each rung is formed by a different astrophysical milestone such as Cepheid variable stars and Type I supernovas. How bright these objects are can tell us their distances, which we can then compare to their redshift values to determine how much the universe has expanded while their light has been traveling to us. However, the problem is, this method gives us a completely different value of the Hubble constant, somewhere around 73.2 kilometers per second per megaparsec. The apparent paradox between the two measurements is what cosmologists have started calling the Hubble tension. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. One possible explanation is that there is a measurement error on the bottom rung of the cosmic distance ladder, which is home to the Cepheid variables. These are stars with luminosities that predictably fluctuate as the stars pulse in and out. The longer the pulsation period between moments of maximum luminosity, the greater that maximum luminosity is. This period luminosity relation allows us to accurately calculate their distances to Earth. It's possible to measure the pulsation period to calculate maximum luminosity. Then, based on how bright a Cepheid variable appears in the sky to us, we can work out how far away it must be to appear that bright. But it's not quite a foolproof method. The Hubble Space Telescope is able to observe Cepheid variables in distant galaxies, but the more distant they are, the harder they become to distinguish among all the other stars that crowd around them. As such, there was a concern that unresolved stars adjacent to Cepheid variables in these faraway galaxies were adding to the Cepheids' apparent brightness values, creating an unseen and systematic error in the measurements. Interstellar dust can also affect the brightness of Cepheid variables, dimming them from our vantage point on Earth. But new measurements achieved with the James Webb Space Telescope of 5 galaxies hosting a combined total of more than 1,000 Cepheid variables have ruled this possible error out. James Webb's infrared vision is able to cut through the interstellar dust, while its greater resolution allows it to clearly resolve the Cepheid variables so they stand out from the crowd. The 5 galaxies observed by James Webb, the most distant of which is NGC 5468, at 130 million light-years from us, have also hosted a combined total of 8 Type Ia supernovas over recent decades. These supernovas, which signal the destruction of white dwarfs, have a standardizable luminosity curve and form the next rung on the cosmic distance ladder above Cepheids. Because the preceding rung is required to calibrate the next rung, Webb's observations of Cepheid variables therefore makes the distance measurements using Type 1 a supernovae, which are bright enough to be seen in much more distant galaxies than Cepheids, more accurate. And they too tell us that there is a contradiction in the different measurements of the Hubble constant. From these Webb's measurements, astronomers led by Adam Rees of Johns Hopkins University determined that Hubble's original measurements were spot on. In the words of Rees, we've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence. What remains is the real and exciting possibility we have misunderstood the universe. We need to find out if we are missing something on how to connect the beginning of the universe and the present day. In other words, the tension at the heart of cosmology is here to stay. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution that would have implications far beyond the world of science. After all, there is no question that we have made incredible progress in understanding our universe, its history, and its origin. But it is also undeniable that we are profoundly puzzled, especially when it comes to the earliest moments of cosmic history. We have no doubt that these moments hold incredible secrets and perhaps the keys to a new scientific revolution. But our universe holds its secrets closely. It is up to us to coax those secrets from its grip, transforming them from mystery into discovery. In a recent remarkable finding, James Webb has discovered that early universe galaxies must have grown up way faster than expected. Plus, the same team also found that 10 billion years ago, the cosmos wasn't quite as disordered and chaotic as previously believed. The international team, led by researchers from Durham University in the UK, reached these conclusions by discovering evidence of structures called star bars, forming in galaxies that existed just a few billion years after the Big Bang. Star bars are elongated regions of increased star density found at the hearts of spiral galaxies like the Milky Way and other disk galaxies. As they form, star bars push gas toward the hearts of their respective galaxies, thereby regulating starbirth. The presence of these central bar structures thus indicate that a galaxy has entered a more settled and mature phase. As Zoe LeConte, team leader and a researcher at Durham University, said in a statement, "Galaxies in the early universe are maturing much faster than we thought. This is a real surprise because you would expect the universe at that stage to be very turbulent, with lots of collisions between galaxies and a lot of gas that hasn't yet transformed into stars. However, thanks to the James Webb Space Telescope, we are seeing a lot of these bars much earlier in the life of the universe, which means that galaxies were at a more settled stage in their evolution than previously thought. This means we will have to adjust our views on early galaxy evolution. Notably, this isn't the first time scientists have gone bar hopping in the early history of the 13.8 billion-year history of the universe. The Hubble Space Telescope witnessed these features as well, but that orbiting eye on the universe could only go as far back as 8 billion to 9 billion years. However, the increased sensitivity and wavelength range of James Webb has stretched such observations back at least another 1 billion years. This has revealed bar formation in galaxies that are seen as they were between 8 billion and 11.5 billion years ago. In fact, of 368 disk galaxies the team considered for the study, 20% already had bars. That is double the number observed by Hubble. The further back in time the team looked with James Webb, the fewer bar structures they observed in galaxies. They believe this could be because galaxies at earlier stages of the universe were not as well formed. An alternative may be that shorter bars were more common in progressively earlier galaxies. Even the impressive observational power of James Webb isn't sufficient to see these short bars in early galaxies. With these results in hand, the team now wants to use the telescope to peer even further back into cosmic time, looking back as far as 12.2 billion years ago. This could reveal whether bar growth was common just 1.6 billion years after the Big Bang. As Gadati concluded, the simulations of the universe now need to be scrutinized to see if we get the same results as the observations we've made with the James Webb Space Telescope. We have to think outside of what we thought we knew. In another observation, the Webb telescope has discovered the oldest dead galaxy ever seen. But the cosmic corpse has left scientists puzzled as it defies explanation by our current knowledge of the early cosmos. The galaxy suddenly and mysteriously halted star formation when the universe was just 700 million years old, when countless stars were birthing thanks to an abundance of pristine gas and dust elsewhere in the universe. The galaxy, named JADES GS Z701QU, and described in a paper published in the journal Nature, provides astronomers with a peek into the elusive underpinnings of galaxy evolution in a primordial universe, including why galaxies stop forming new stars and whether forces driving their starbursts alter across epochs. In the words of study lead author Tobias Lusser, a researcher at the University of Cambridge's Kavli Institute for Cosmology, Cambridge or KICC, galaxies need a rich supply of gas to form new stars, and the early universe was like an all-you-can-eat buffet. Current models cannot explain how the newfound galaxy not only took shape in less than 1 billion years after the Big Bang, but also shut down its star factory so quickly. According to study co-author Francesco Diogenio, also a researcher at KICC, it's only later in the universe that we usually start to see galaxies stop forming stars. In comparison, a handful of other dead galaxies found elsewhere appear to have paused forming new stars when the universe was about 3 billion years old. To discover JADES GS Z701QU, Lusser and his colleagues used James Webb's powerful infrared vision to peer through the thick veil of dust obscuring the earliest objects in the universe. In addition to being the oldest dead or quenched galaxy spotted so far, the newfound galaxy is also many times lighter than other similarly quiescent galaxies previously found in the early universe. Webb's data suggest the galaxy intensely formed stars for somewhere between 30 million to 90 million years before it rapidly shut off, although precisely what ended it is still unknown. Astronomers know of a couple different factors that can slow down or extinguish star formation. For instance, turbulence inside a galaxy, such as radiation emitted by a supermassive black hole, can push gas out of the galaxy and starve it of the gas reservoir it relies on to form stars. Another intriguing possibility is that the galaxy's surroundings at the time did not sufficiently replenish the gas reservoir being consumed by birthing stars, leading to a deficit in star-forming material. However, in the words of study co-author Roberto Maiolino, an astrophysicist at KICC, we're not sure if any of those scenarios can explain what we've now seen with Webb. Current models based on the modern universe are unable to explain the properties of JADES GS Z7901QU, suggesting they may need to be revisited. Another possible explanation for the new galaxy's dormancy could be that galaxies in the early universe die and then burst back to life. However, previous research of dead galaxies from when the universe was around 3 billion years old, a time of its most prolific star birth, suggested such dead galaxies cannot rejuvenate even via mergers with nearby galaxies, which instead only serve to puff them up. As Eugenio said, we'll need more observations to help us figure that out. A quick note, James Webb now is digging deep into the mysteries of gas planets. More specifically, the researchers say they've started making headway in answering the question of how long gas giants likely have to form around their host stars before all the gas around those stars fades away. The short answer is not very long, but the full story is far more nuanced. The research team used the Webb telescope to probe what's a little confusingly known as the disk wind. This doesn't really refer to a wind like you may imagine. Rather, it refers to the process of gas leaving a disk around a star. This disk would be one filled with different types of material with the potential to give rise to planets. It's thus otherwise known as a protoplanetary disk. According to Naman Bajaj, lead author of the new disk wind analysis and a scientist with the University of Arizona's Lunar and Planetary Science Laboratory, we knew that they exist and that they might play an important role in disk evolution. What we didn't know was the underlying physics, and consequently, how much mass is being lost. These are key to answering all our questions on its impact. Such a disk would include non-gaseous debris too, to be clear, like dust that can come together over time to create rocky planets. That's actually how Earth is believed to have formed once upon a time. Though Bajaj and fellow researchers didn't come up with a final, tightly confirmed answer as to how long gas planets may have to form before protoplanetary disk gas depletes fully, he did offer a ballpark based on his calculations. According to Bajaj, considering the gas mass in this disk, and assuming that the gas will keep leaving at this constant rate that we find, about 1 moon mass every year, it will take approximately 100,000 years. Yes, that sounds like a long time. But, as Bajaj emphasized, it's an incredibly short timescale in astronomical terms. A protoplanetary disk lives for about 5 to 10 million years. After all, though it's severely cliché to say at this point, all of this is a testament to how much the James Webb Space Telescope is revolutionizing our understanding of the universe. Its infrared sensitivity is immense for sure, but a lot of its discoveries owe themselves to the body of work already available to build on. The library of papers that's been helping scientists decide where, precisely, James Webb should look. Cosmology has changed forever with the launch of James Webb on Christmas Day 2021. Ever since it opened its impressively sharp, high-resolution infrared eyes, James Webb looked back at some of the earliest stages of the universe, gathered sharp, pristine, and beautiful insights of early star and galaxy formation, and provided insights into the formation of planetary systems, including our own solar system. But in some sense, James Webb was almost too good, far exceeding all hopes and expectations. Astronomers expected to find some of these infant galaxies with Webb, but they didn't expect to find so many. Webb's unprecedentedly deep views revealed a colossal surprise: a bunch of the impossible early galaxies, Even at these earliest times, these galaxies were too big, bright, and numerous to explain, some of which are even older than the universe. Our best cosmic predictions, based on lambda-cold dark matter, the standard model of cosmology, didn't expect what James Webb saw. In other words, discoveries made by James Webb could shake their understanding of galactic history. So, is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb just found massive structures that could defy our current theories of the universe. The farther and farther back into the distant universe we look, we have a picture of what we expect to see. At some point, we should find the first and earliest bright, large, luminous galaxy, and we should see their number density rapidly decrease as we approach that limit. Before that, we should find only smaller and less evolved galaxies, decreasing in number and number density until we find the very first among those. Before that, we should only see individual star clusters and proto-galaxies, and these should be extremely blue and primitive, and again should only exist in low number densities the farther back we go. And finally, there should truly be a time where the very first stars and star clusters of all appear, and beyond that, there should be no luminous sources at all to observe, excepting the Big Bang's leftover glow itself. When we look into these deep depths of the universe and examine these galaxies, we're basically asking the universe, how did you grow up and come to be the way you are today? Given that we have a model of the universe, a mix of dark matter, normal matter, dark energy, and a little bit of radiation, we can arrive at predictions for what we expect to see in the universe at any given time. Looking at these distant objects with the James Webb Space Telescope, and with its spectroscopic capabilities in particular, allows us to test that model, and to see if we truly understand the universe we inhabit, or if, and how, we have to revise our picture of the cosmos. The James Webb Space Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena. But perhaps its greatest scientific contribution is its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb's SEERS, or Cosmic Evolution Early Release Science Survey, are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies, dating back as much to just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. According to Michaela Bagley of the University of Texas, one of the leading SEERS researchers, the theoretical models didn't predict that these should be there. We still don't yet know how you can see a galaxy that bright, that early. One particular galaxy jumped out of the SEERS data straight away. Maisie's galaxy, named after the daughter of Stephen Finkelstein, one of the researchers, is 13 billion years old, making it one of the oldest galaxies ever observed. And it is much brighter and much bluer than anyone predicted. As Bagley said, when we found Maisie's galaxy, the surprising part was, how is it in the universe? It's exciting that this is the universe we live in. It's a universe with a ton more galaxies than we thought. Webb is able to detect extremely distant galaxies because its instruments operate in the infrared wavelength. A small handful of extremely distant galaxies had been detected previously by the Hubble Space Telescope, which operates primarily in the optical light wavelength, which is equivalent to what human eyes can see. But as galaxies move further and further away from us, due to the expansion of the universe, their light is shifted toward the red end of the spectrum in a process called redshift. The extremely distant galaxies that early universe researchers are interested in have light that is redshifted so far that it is no longer visible in the optical and can only be seen in the infrared. So Hubble's instruments were pushed to the limits to detect even a few of these galaxies, while Webb was able to detect many of them incredibly quickly, within a few days of the telescope beginning its science operations. When discussing these galaxies, scientists typically talk about them in terms of their age rather than their distance. You'll see researchers describe a galaxy as being from the first few 100 million years after the Big Bang rather than being located billions of miles from Earth. That's also because of the expansion of the universe, which creates a moving frame of reference that makes it hard to describe distance meaningfully. Examples include galaxies like Maisie's galaxy, which is described as being 13 billion years old. The light has traveled 13 billion years to get to us, but if we could see Maisie's galaxy today, it is much, much further away because in that time, the universe has kept expanding and accelerated its expansion. The time the light has spent traveling to us gives us more concrete information about when in the universe we're observing these galaxies. Initial estimations of the redshift, and thus age, of Maisie's galaxy were based on photometry, which works by analyzing brightness in images while using a small number of wide-frequency filters. These calculations suggested the galaxy had a redshift of 11.8, but Finkelstein and the Sears team wanted a more accurate age estimation. To do this, they made follow-up observations with James Webb's near-infrared spectrograph, or NIR spec for short. This allowed Finkelstein and colleagues to look at spectral lines created in light data, dictated by the absorptions and emissions of chemical elements at specific wavelengths. From there, they could pinpoint the actual redshift of Maisie's galaxy. It appeared to be 11.4. This means Maisie's galaxy is technically seen more recently in the universe than initially estimated, by a factor of tens of millions of years. Nonetheless, it is still considered immensely old. The James Webb captured the galaxy as it was just 390 million years after the Big Bang. This impressive age places Maisie's galaxy among the 4 oldest galaxies in the universe that have had their ages confirmed by spectroscopy, a technique that splits light into its component frequencies to better reveal its brightness, heat, and chemical composition. While such galaxies don't yet pose problems for leading models of cosmology, they suggest galactic formation began earlier and proceeded faster than expected in the universe, which theorists had previously predicted began churning out galaxies at the ripe age of 1 billion years after the Big Bang. As Fabio Pacucci of the Harvard-Smithsonian Center for Astrophysics said, "We're seeing a rise of massive galaxies faster than we thought previously." The ages of some of these early galaxies are estimated at just tens of millions of years. This could have implications for large structures of dark matter known as halos that sculpted early galaxies, and for the nature of dark matter particles themselves. One of the big open questions is, what is dark matter, says Sandro Ticella of the University of Cambridge. The first generation of galaxies is a sensitive probe for different dark matter models. On the other hand, we should be cautioned that some problematic and potentially model-busting early universe candidate galaxies still remain. Scientists had already produced models of what early galaxies would be like, and Webb contradicted them almost immediately. As soon as James Webb began looking for early galaxies, it found far more of them than anyone had predicted, and found that they were much brighter too. Light is a double-edged sword in the context of these galaxies. It's what lets us study the galaxies. But there's so much more of it than astronomers would have expected. The brightness of a galaxy can be related to its mass, because a galaxy's light comes from stars. If you assume a certain average brightness and mass of a star, you can roughly estimate the mass of a galaxy. But much of the modeling astronomers have done up to this point has led them to believe that there wasn't enough time for galaxies to get this massive in so little time. According to Jorge Moreno, an associate professor of astronomy at Pomona College, it's like if you went to a kindergarten and you saw a teenager. What's more, today, most galaxies are separated into two types: spirals, which are disk-like with arms of dust and gas, and ellipticals, which are more like spheres of smooth light. Until now, scientists thought that any galaxies from this relatively early period in the history of the universe would have been too young to have been forced into that binary yet. Instead, astronomers thought the galaxies would be blobs. But under James Webb's views, some of the early galaxies look a lot like galaxies in the local universe. They seem to have added structure and maybe even spiral arms. That wasn't something we really expected. The high level of structure and brightness in these galaxies is leading some astrophysicists to question the age of the universe. In an attempt to explain the impossible massive galaxies existing so early in the timeline of the universe, a researcher has posited that the universe is roughly twice as old as previously believed. They pushed the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. That's an interesting scenario, but it doesn't correspond to the evidences at hand. So, up to now, there's currently no consensus on what is the root of the discrepancy between the models we have and the data we observe with Webb. The answer could be related to dark matter and its role in the early universe, or it could be that the way early galaxies were formed was spurred on by forces that haven't been considered yet. However, it's worth noting that even before the James Webb Space Telescope, scientists knew that the early universe was a very different place from the universe today. Its galaxies were made almost entirely of hydrogen and helium, were shaped by tendrils of dark matter, and hosted enormous bright stars that lived fast and died young. While the laws of physics haven't changed over the past billions of years, the scale of the universe has, and that affects how those physical laws apply to galaxies. When the universe was smaller and denser, that affected the ways in which stars form in complex ways. As Bagley explained, if the universe is smaller, the density inside galaxies and outside galaxies is probably higher. If it's dense and hot, the gas won't collapse to form stars. If it's dense and cold, then you could get a ton more stars. Another way in which the early universe was fundamentally different is in its overall chemical composition. Heavy elements like metals were almost entirely absent in the early universe, because these elements were primarily formed within stars and spread by their explosive deaths, called supernovae. It took several generations of stars to spread these heavier elements through the universe and to be absorbed into stars similar to those we see today. The hypothetical earliest stars in existence are referred to as population 3 stars. Today's young stars are population 1 stars, and the numbering counts backward in age. They were much bigger, heavier, and bluer than stars today, and they gave off more ionizing radiation. Those differences are because of the way stars generate heat and light in a process called fusion. If a star is made only of hydrogen and helium, to do fusion, the star has to be hotter and denser than a star that has carbon, nitrogen, oxygen, Bagley explained. There's a different chemical pathway to create fusion, and that requires a larger size and more mass to support it. No one has ever observed a population 3 star before, and finding one is one of the holy grails of modern astronomy. But scientists believe it could be possible to find one using Webb. Anyway, James Webb was built primarily to transform our understanding of the early universe. And telltale evidence gathered by the James Webb Space Telescope suggests we're closer than ever before to finding elusive first stars of the universe. All of this discussion of billion-year-old history might seem rather abstract, but in fact, it's directly relevant to understanding the universe as we see it today, and as the James Webb Space Telescope is revealing in greater detail than ever before. That's because astronomy operates on such long time scales that we can't watch objects like galaxies across their lifespans. Most galaxies we see around us today look like the Milky Way, but we can't see them develop over time. To study that development, we need to look for distant and ancient galaxies, which Bagley refers to as baby pictures of the Milky Way. This is all about understanding how our Milky Way formed. It sounds cliché, but before we can understand where we are and where we're going, we need to understand where we came from. In addition, on the hunt for alien civilization, NASA has just revealed that 17 discovered exoplanets could house subsurface oceans buried below thick sheets of ice. These worlds, much like the icy moons of Jupiter, could therefore be promising places to search for biosignatures, chemical signs of life. While the exact composition of these worlds remains unclear, estimates of their surface temperatures from previous studies point them being significantly colder than Earth. They're also each less dense than Earth, despite being roughly the same size as our planet. As Lynn A. Quick of NASA's Goddard Space Flight Center said in a statement, "Our analyses predict that these 17 worlds may have ice-covered surfaces but receive enough internal heating from the decay of radioactive elements and tidal forces from their host stars to maintain internal oceans." In other words, while their host stars may not provide conditions warm enough to keep water in liquid form on their surfaces, these planets may exhibit processes that can generate heat below their surface. The stretching and compression of rock inside a planet as it gravitationally interacts with its sun, for instance, could provide significant amounts of internal heat, enough to sustain a subsurface ocean. The radioactive decay of heavy elements inside the core of a planet can provide intrinsic heat as well. Thanks to the amount of internal heating they experience, all planets in our study could also exhibit cryovolcanic eruptions in the form of geyser-like plumes. Quick said, cryovolcanism meaning, in short, ice volcanoes. The study drew on what we know from the geyser activity of two of Jupiter's moons, Europa and Enceladus. Two of the exoplanets named in the research, Proxima Centauri b and LHS 1140b, were particularly promising candidates for having oceans relatively near the surface. Since our models predict that oceans could be found relatively close to the surfaces of Proxima Centauri b and LHS 1140b, and their rate of geyser activity could exceed Europa's by hundreds to thousands of times, telescopes are most likely to detect geological activity on these planets, said Quick. Follow-up observations of these worlds will likely include astronomers capturing the emission spectra of light traveling through these planets' atmospheres. Chemicals and molecules erupted into the atmosphere from cryovolcanic activity may hold clues as to whether life might exist in the cold, dark depths of these worlds. In a one-of-a-kind event, scientists just announced that Mars's atmosphere, once as thick as if not thicker than Earth's today, is leaking into space. About 0.11 kg of Mars' atmosphere is pushed away every second by the incessant solar wind, the speedy stream of charged particles routinely blasted from the sun, which pervade the solar system and even reach beyond Pluto. But for a rare 2 days last December, some of that wind went away. Its sudden and dramatic disappearance caused the atmosphere on Mars's sun-facing side to swell by nearly 4 times its usual size, from its usual 800 kilometers to over 3,000 kilometers. The peculiar event was recorded by a NASA orbiter named MAVEN, short for Mars Atmosphere and Volatile Evolution, which has been observing both Mars's atmosphere and its response to the sun's behavior since 2014. MAVEN's data showed other aspects of the Martian system, including the teardrop-shaped magnetosphere, the bow shock, and the ionosphere, expanded similarly. As Jasper Halikas, a professor of physics and astronomy at the University of Iowa and a member of the MAVEN team, said, "We're really off the charts here. This is something that we haven't seen at Mars before with MAVEN." The atypical episode, the first in nearly a decade of MAVEN's career, occurred after a fast-moving region of a solar wind overtook its slower counterpart and swept up the latter's material, leaving behind a sparse region. The emptied storm reached Mars on Sector 25, 2022, giving scientists a thrilling front-row seat to watch the planet's atmosphere balloon out, the way it might have been if it were circling a less windy star. According to Halekas, who is leading a new study, this was a Christmas present for us. Nature set up this perfect science experiment. With Maven's data of the unexpected dynamics on Mars, Halekas and his colleagues studied how extreme solar events and their absence influence the planet's atmosphere, an insight valuable to understanding its evolution. The findings also have implications for our understanding of Earth-like planets outside our solar system and how they interact with their host stars, the team shared on Monday. We could look under the hood at what physics is going on, how the dynamics are working, and really get a sense of those details, said Maven team member Skylar Shaver of the Laboratory for Atmospheric and Space Physics in Boulder. 2 days after the almost vacant storm passed Mars, the atmosphere around the red planet settled down to its original state once again, but not before bouncing a little like a jiggling plate of jello. A similar storm struck Earth in 1999, when our planet's atmosphere grew to 5 times its normal size. But there aren't often orbiting spacecraft positioned as well as Maven is now to study such events, the new atlas reported. Shannon Curry, the principal investigator for the Maven mission, suspects events like this were common during Mars' early evolution 3 to 4 billion years ago, when our sun was more fiery than it is now and perhaps blasted out storms once a week or even every day. Such extreme events were likely responsible for parching the red planet, a world scientists presume once hosted liquid water and offered conditions friendly toward life. Extrapolating the latest Maven data to study Mars' evolution through time could shed light on how much its atmosphere eroded away and how fast the planet dried up, Curry said. Curry added events like this may occur multiple times in the next 2 years as the sun's activity climbs to its peak, expected to occur in July 2025, if not late next year. Last, as a piece of good news, the Hubble Space Telescope, following a string of setbacks concerning one of its directional instruments, has now resumed its job of capturing deep space images. NASA confirms that in a statement posted to the Hubble Space Telescope blog. The telescope's issues all began on November 19th, when one of the iconic observatory's 3 gyroscopes, a trio that live on from an original set of 6, began providing faulty readings. In general, gyroscopes are devices that use either circulating beams of light or rapidly spinning wheels to help scientists make sure an object is facing the direction they want it to face. Incorrect gyroscope readings on the Hubble telescope, as you might imagine, can therefore drastically affect science measurements. To image a specific spot in deep space with this Earth-orbiting telescope, you'd have to make sure it's actually facing that spot in deep space. Thus, Hubble entered safe mode on November 19th, something that's programmed to happen automatically when certain issues arise with the observatory. The team, however, was able to bring it back online the following day. But things weren't looking good shortly after, when gyro issues sent Hubble into yet another safe mode situation on November 21. The team brought Hubble back once more, shortly after that, only for the beloved telescope to retreat into its dark corner once again on November 23rd. That most recent safe mode entrance was slightly worrying as it persisted for longer than the previous 2 dips. It wasn't too worrying though, because first of all, this isn't the first time Hubble's gyros have raised issues leading to a shutdown. And secondly, maybe most importantly, the observatory can actually function with only 1 gyroscope. The team just uses 3 because it maximizes efficiency. Though it's been over 3 decades since Hubble began exploring the vibrant reaches of our universe, and though a new observatory in town has been catching most of the spotlight recently, this Reynolds Wrap-looking telescope is surely not finished yet. Most of us are familiar with the standard narrative of how the universe began. There was an infinitely dense point of an infinite temperature with no size called a singularity. This singularity exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 to the power of -36 seconds and 10 to the power of -32 seconds, space expanded exponentially, growing much, much larger in size. After this period, space continued to expand, but at a much slower rate, and eventually, we see the universe that we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. But for a few physicists, the premier theory doesn't paint an accurate picture of the evolution of our universe. Rather, they say that the universe existed before that point, stretching forever into the past as well as the future. While the universe is expanding today, it was contracting in the time before the Big Bang. In this picture, the Big Bang isn't so much a bang, but a bounce, a moment when a shrinking universe reversed course and began to grow. And according to their theory, the universe could bounce again. Today's expansion could be followed by collapse in the far future, followed by another bounce. Some physicists have suggested this bouncing could be infinite. This, of course, is counter to the way most cosmologists see it, where everything started with the Big Bang. But what is noteworthy here is this is not the only theory that dares to challenge the pinnacle theory of cosmology. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing. Adding a bit of tension, the James Webb telescope has made a bunch of unexpected discoveries that contradict the notion that the Big Bang marked the beginning of the universe. All of these raise a question. If the Big Bang wasn't the beginning of the cosmos, then what was it? Could the universe start with a bounce, or something else entirely? Join us as we dig deep into one of the thorniest in physics. The idea that the universe had a beginning, or a day without a yesterday, as it was originally known, goes all the way back to Georges Lemaitre in 1927. Although it's still a defensible position to state that the universe likely had a beginning, that stage of our cosmic history has very little to do with the hot Big Bang that describes our early universe. Although many laypersons and even a minority of professionals still cling to the idea that the Big Bang means the very beginning of it all, that definition is out of date. The Big Bang now is not the birth of time and space. We know that today, in 2023. In fact, there's a ton of evidence that points to a non-singular origin to our universe. We never achieved those arbitrarily high temperatures. There's a cutoff. Instead, our universe is best described by an inflationary period that occurred prior to the Big Bang. And the Big Bang is the aftermath of what occurred at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty. There were no particles, no matter, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time, by about 1 part in 30,000 on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new, small-scale fluctuations are created atop them. This superposition of fluctuations, of small scales atop intermediate scales, atop large scales, atop superhorizon scales, is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on. But inflation will come to an end randomly, and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang, before that region disappeared entirely from view. In an initially relatively small region, perhaps no bigger than a human-sized hamster ball, but perhaps much larger. The energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately 10 to the power of negative 33 seconds or so. A brief amount of time, but nonetheless one that is not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise, from just a few degrees above absolute zero to perhaps 20 Kelvin or so, over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All quanta will behave as radiation with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive. It doesn't matter under these conditions. This conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly as time goes on. But when inflation ends, the universe reheats, and the hot Big Bang starts, more distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate there drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, that distance doubles yet again and again and again. The process is relentless. But once the Big Bang begins, all of that changes, as the expanding universe immediately slows down once the first moment of expansion elapses. Probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation, and expand more slowly than the still inflating regions do, leaving you, in the inflating region, as a typical region within space-time dominating its volume. These regions, where hot Big Bangs occur, will expand away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view. In the standard inflationary picture, because of this expansion rate change, there's virtually no chance that any two universes, where separate hot Big Bangs occur, will ever collide or interact. Finally, the region where we will come to live gets cosmically lucky, and inflation comes to an end for us. The energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and the only departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. But that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early on. The first one we've ever accessed comes from 380,000 years later, after they've undergone countless interactions. Even at that, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations that are imprinted on the first picture of the universe, the cosmic microwave background, give us confirmation of how the Big Bang began. However, there are a lot of inconsistencies between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summarized in 4 anomalies. First, on very large scales, the universe isn't acting like we think it should. Second, light from the cosmic microwave background will be lensed by matter in between us and the cosmic microwave background. This means that matter acts like a giant lens, bending and changing the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem, it has sometimes been called a crisis for cosmology. Third, the two hemispheres of the cosmic microwave background sky have different average temperatures. This doesn't make a lot of sense, since we believe that the universe should have started out uniform, on average. And last, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from more nearby Cepheid stars. Taken together, these anomalies mean we're missing something fundamental in our understanding of the universe. The answer may lie in loop quantum cosmology. Loop quantum cosmology arises from loop quantum gravity. In loop quantum gravity, gravity itself is made of particles called quanta. These quanta come together to form the fabric of space and time. In this model of the universe, there is a smallest size of space itself, the Planck scale, or 10 to the power of negative 35 meters. Nothing, not even space itself, can be smaller than this. This means that the Big Bang couldn't exist in a universe with loop quantum cosmology. The universe could never get down to an infinitely small, infinitely dense point. Close to the Big Bang, when the universe was very small, really weird things happen mathematically. Infinities start to arise and threaten to tear the fabric of space-time itself. It's at these locations where loop quantum gravity can come in to provide corrections to the physics we already know. As Dr. Abhay Ashtekar at Penn State University, who led a study showing that the universe started in a bounce rather than a bang, said, "At such places, one has to use quantum geometry underlying loop quantum gravity. The quantum-corrected equations predict that there is an effective repulsive force. This means in these regions, when the universe is very small, the repulsion would result in a bounce. If our universe originated in a bounce, that means there was another universe before us. That universe went through its life, perhaps expanding and eventually contracting once again. As all of the matter and space-time of this universe came together, it ended in a spectacular fireball. Then, in a giant bounce, our universe was born, like a phoenix rising from the ashes of the old universe. This isn't entirely a new idea. Physicists have tossed around the idea of the Big Bounce for several decades. Even farther back, cyclic time is present in Hindu cosmology. If loop quantum cosmology is the correct model of the universe, in its infancy, the universe would have had very high curvature. To visualize this, think of a globe has positive curvature, a sheet of paper has flat curvature, and a saddle has negative curvature. If the universe was strongly curved when it was young, evidence of this would show up in the cosmic microwave background. When you look at the cosmic microwave background, you realize that it is not uniform. It's close, but there are small differences in temperature from one point in the sky to another. If you plot these temperature differences as a function of scale, you get one of the most powerful tools of cosmology, the angular power spectrum. Evidence of the curvature of the early universe would show up in the angular power spectrum of the cosmic microwave background. Some of these effects would show up at extremely large scales, larger than the size of the universe. This is a problem, obviously. We won't be able to observe it. However, luckily for us, these large scales interact with smaller scales, providing us with indirect evidence of this early phase of the universe. One of the effects of these interactions is to create the hemispherical anisotropy, says Ashtekar. In our current understanding of the universe, the probability that the two hemispheres of the sky would be different is very small. But with loop quantum cosmology corrections, the probability is enhanced and the observed anisotropy is no longer anomalous. That means that loop quantum cosmology would provide an explanation for anomaly number 3, why the hemispheres in the sky have different average temperatures. In addition, using the model of the universe that loop quantum cosmology provides, solves the first two anomalies that we have seen in the cosmic microwave background: strange behavior at large scales and lensing. According to Dr. V. Srinath of the National Institute of Technology, Karnataka, this possibility that cosmic microwave background anomalies are not just statistical flukes, but rather effects due to quantum gravity happening very early in the universe is very exciting. But how sure are we that the universe originated in a big bounce? Except that, with all major claims, extraordinary evidence is needed. The idea that the universe originated in the Big Bounce has been suggested several times. We'll have to see if this one sticks. Another problem: our observations are limited, and it may just be that we are observing a part of the universe that is unusual. That's a problem called cosmic variance. As Dr. Donghui Zhang, a co-author of the paper and professor at Penn State University, said, "It is hard to confirm with 100% confidence because of the cosmic variance. But what is intriguing is that including this new possibilities can resolve two issues at the same time: the large-scale power suppression and small-scale lensing amplitude. Ruling out signs of in-loop quantum cosmology-driven cosmic bounce in Planck data means the cosmic microwave background anomalies remain unexplained. But an even larger cosmic issue lingers. Did the universe have a beginning at all? As far as advocates of the Big Bang are concerned, it did. But that leaves us with the inscrutable singularity that started everything off. Alternatively, according to theories of so-called cyclic cosmologies, the universe is immortal and is going through endless bounces. Although a bouncing universe may experience one or more cycles, a truly cyclic universe has no beginning and no end. It consists of a series of bounces that go back for an infinite number of cycles and will continue for an infinite number more. And because such a universe doesn't have a beginning, there's no Big Bang and no singularity. But physicist William Kinney of the University at Buffalo points out that there is a critical flaw lurks in the idea of an eternally cycling universe. That flaw is entropy, which builds up as a universe bounces. Often thought of as the amount of disorder in a system, entropy is related to the system's amount of useful energy. The higher the entropy, the less energy available. If the universe increases in entropy and disorder with each bounce, the amount of usable energy available decreases each time. In that case, the cosmos would have had larger amounts of useful energy in earlier epochs. If you extrapolate back far enough, that implies a Big Bang, like beginning with an infinitely small amount of entropy, even for a universe that subsequently goes through cyclic bounces. If you're wondering how this scenario doesn't violate the law of conservation of energy, we're talking about available energy. Although the total amount of energy in the cosmos remains static, the amount that can do useful work decreases with increasing entropy. New cyclic models get around the problem by requiring that the universe expands by a lot with each cycle. The expansion allows the universe to smooth out, dissipating the entropy before collapsing again. Although this explanation solves the entropy problem, Kinney and his University at Buffalo co-author Nina Stein calculated in their recent paper that the solution itself ensures that the universe is not immortal. As Kinney says, "I feel like we've demonstrated something fundamental about the universe, which is that it probably had a beginning. That implies a Big Bang occurred at some point, even if that event happened many bouncing universes ago, which in turn suggests that it took a singularity to get everything going in the first place." Kinney's paper is the latest in the debate over cyclic universes, but proponents of a universe without beginning or end have yet to respond in the scientific literature. Two leading proponents of a cyclic universe, astrophysicists Paul Steinhardt of Princeton University and Anna Ijas of New York University, declined to comment for this article. If the history of the debate is any indication, though, we may soon hear of a workaround to counter Kinney's analysis. Some physicists say the Planck data only rule out a bounce under a loop quantum cosmology model that can explain away the cosmic microwave background anomalies through the bispectrum, not other loop quantum cosmology bounce models that address anomalies using different mechanisms. Cosmologist Nelson Pinto Neto of the Brazilian Center for Physics Research, who has studied bouncing and other cyclic models, agrees that loop quantum cosmology bounces that account for the cosmic microwave background. Anomalies are likely off the table now, but he's more sanguine on the question of a cyclic universe. According to Nelson, existence is a fact. We are all here and now. Non-existence is an abstraction of the human mind. This is the reason he thinks that a cyclic universe, which has always existed, is simpler than one that has been created. However, as a scientist, he must be open to both possibilities. While the origin of our universe is still a mystery, there was a contentious argument about how the universe would end. The details of this narrative depend on the kinds of stuff the universe contains. The cosmic recipe determines how the universe changes in time and what kind of future it will have. There are essentially two possibilities. In one, the universe will keep on expanding forever, because stars have finite lives. At some point far in the distant future, they will be extinct. Stellar corpses will dot the universe, from slowly smoldering white dwarfs to black holes of different sizes. But drama can be added here, depending on what kinds of matter the universe contains. If the current recipe remains viable, there are three main ingredients: dark matter, dark energy, and the stuff we are made of, the normal matter of protons and electrons. Assuming normal matter and dark matter are stable in the long term, dark energy controls the future of the universe. If dark energy, this ether-like substance of unknown composition, is a constant, that is, if its density does not change and it maintains a fixed volume irrespective of cosmic expansion, then the universe's expansion will keep on accelerating. In extreme scenarios, it may have so much negative pressure that it will rip everything apart, decomposing matter back into its basic ingredients. Instead of from dust to dust, the cosmic epitaph would be from particles to particles. But it is also possible that dark energy is not like that, and that its negative pressure will fade with time, no longer fueling the universe's rapid expansion. Acceleration will lose pace, and the universe will retain the faded stars and their corpses, all resting far from each other, the ultimate cosmic loneliness. The sad part is that in a cosmos without room for entropy to grow, matter cannot reorganize into anything interesting. This is the cold cosmic death scenario. If nothing changes, time itself loses its function and reaches an end. Another possibility is that the expansion will slow down. If there is enough matter out there, it may revert itself and push the universe from expansion into contraction. Eventually, matter that was dispersed for billions of years will compact back into a small volume, heat up, reach crushing densities and, well, it depends. It may go into a big crunch, the inverse of the Big Bang, or it may reach a point of maximum contraction and then bounce outward into a new phase of expansion. This is the bounce universe model, where the universe trades periods of expansion and contraction, never quite reaching the point of infinite density or initial singularity. Time keeps on ticking, although each cycle needs new clocks. Every end of time marks the beginning of a new time, a new cycle of existence. This is a bit more comforting a view than cold death, even if each cycle involves destruction by fire. What we learn from our current cosmological models is how fortunate we are to exist precisely when it is possible to exist. Of course, there is no luck involved here. We exist now because this is when it is possible for matter to agglomerate into thinking blobs like us. In other eras, there would be no stars capable of sustaining life long enough for it to conjecture about its fate. So if time will end, it is because creatures like us will also end. In a universe without sentient beings, aware of time's passage, without the awareness of past and future, the very concept of existence is meaningless. That should give us pause when we consider how small we are in the vastness of space. Small, yes, but as far as we know, we are the ones who hold the whole cosmic history in our minds. Something is awry in the early universe and scientists have no idea about it.
Already in the very early data we obtained nearly 2 years ago. And I think the surprising thing was that it's actually very bright. And so our initial reaction was that, well, it cannot be that distant.
Sometime after the Big Bang, around 12+ billion years ago, when the universe went from a dark, diffuse place full of gas to a light-filled universe populated by stars and galaxies. This is the era that laid the foundation for everything to come, including our solar system and you and me. Scientists had some theories about what happened during this crucial period, but James Webb is giving us a new dictionary to translate the language of the early universe. What James Webb found is too different to fit scientists' current theory of how the universe grew up. This has raised some concerns that the history of the early universe needs to be rewritten.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us as we dig deep into how James Webb just cracked the universe's code. Over the course of the past century, astronomers and physicists have produced an incredibly rich and detailed account of our universe's history. This picture, sometimes called the Standard Model of Cosmology, sometimes called the Inflationary Hot Big Bang, and sometimes called the Lambda Cold Dark Matter Model, has been remarkably successful. This model, initially developed in the early 20th century, has survived a battery of observational tests and is extremely good at explaining a variety of cosmological observations, including the redshifting of light from distant galaxies, the appearance of leftover radiation in the form of the cosmic microwave background, the abundances of light elements, and the evolution of galaxies and larger structures. While the Big Bang Theory can't say for certain which galaxies will appear where, it can talk about probabilities. It predicts that, as we look farther and farther back in time, that is to greater and greater cosmic distances, that the galaxies we see will be inherently smaller, bluer, less evolved, less rich in heavy elements, and that at some point, beyond where we've been able to look, we should cease to see stars or galaxies of any type, as we'll reach the universe's dark ages. But that's simply a picture of what happens. What we need, if we want to compare theory to observations, is to quantitatively figure out not just what happens, but when it happens, and, quantitatively, how much it happens by. Even though the laws of physics are well known, and the starting point, or our initial conditions, are also well known, our best quantitative predictions still come along with a large amount of uncertainty. From the theory of cosmic inflation and the patterns of fluctuations that we see in the cosmic microwave background, we know that our universe began at the start of the hot Big Bang from an almost perfectly uniform state. There were the seeds of structure, density imperfections, imprinted atop that near-uniform background, leading to underdensities and overdensities at about the 1 part in 30,000 level, that were almost but not quite the same on all cosmic scales. About 3% larger on size of the universe scales than on size of a galaxy scales. We know that early on, these imperfections grew gravitationally, but also had to contend with interactions with and pressure from radiation, like photons, creating a pattern of peaks and valleys in how overdense, underdense various regions were on a variety of cosmic scales. Then, the universe forms neutral atoms, about 380,000 years after the hot Big Bang, and expands, cools, and gravitates according to the laws of general relativity. As long as these density imperfections remain small compared to the average density of the universe, it's easy and straightforward to compute how they grow. But as they grow larger, a series of effects all come into play, making the question of how big do they grow and how quickly very assumption dependent. For example, as large amounts of gas begin to accrue in these overdense regions, how efficiently does that gas cool? As these overdense regions grow within the expanding universe, with some small-scale regions superimposed atop larger-scale overdensities. How do these high-density regions interact in these overlapping locations? Some overdense regions will occur close to other overdense regions. How is the growth of structure affected when these regions interact? As normal matter accumulates in the centers of these overdense regions, it slows down, collides, and heats up. As that heat gets radiated away, how does that feedback affect the growth rate of these regions, including both the normal matter and the dark matter? And finally, when stars finally form in these very different environments to the ones we find today, how long do they live? How do they die? How does that impact the normal and dark matter that doesn't become stars? And what implications does that have for subsequent generations of stars and the growth of these early cosmic structures? It's important to understand that the answers to all of these questions are uncertain. They're firmly in the realm of the purely theoretical and are dependent on what details we include and exclude in our models and simulations. Are we using the correct models to identify halos, where a halo represents an individual overdensity in space, or are we incorrectly treating interdependent halos as independent entities or vice versa? Are we modeling the first stars correctly, including their initial mass functions and their death throes, or are they heavier and more likely to directly collapse to black holes than we think? For that matter, do we even need stars to form black holes? Or can these intersecting, inflowing streams of gas form the seeds of supermassive black holes directly, possibly with masses that are millions of times the mass of our sun right away? It's pretty clear that the very first objects, stars, black holes, and star clusters, begin forming no later than about 150 million years after the Big Bang, and perhaps as early as only 50 to 100 million years after the Big Bang. But these ought to be relatively rare occurrences. But now, for the first time, owing to the unprecedented capabilities of the James Webb Space Telescope, we're beginning to discover and characterize unpredicted ancient objects found in these very, very early stages of our cosmic history. But why is the James Webb Space Telescope so good? The short answer is that James Webb is optimized to see in the near and mid-infrared. As light travels towards us from faraway objects, it gets stretched into longer wavelengths, redshifted, due to the expansion of the universe. The light we see from a star near the beginning of the universe took billions of years to reach us. It may have started as ultraviolet or visible light, but by the time it reaches us, it's near and mid-infrared light. So, to see the early universe, we need a telescope like James Webb. Its infrared capability also allows us to peer into dense dust clouds shrouding newly forming stars, giving us an inside view like never before. However, right from its first observations, the Webb telescope has given astronomers new puzzles to solve and new questions to pursue. In particular, it is challenging what we thought we knew about the early evolution of galaxies. James Webb's intriguing deep-field observations of faint light from the early, distant universe reveal stars and galaxies that seem to be much larger than expected. The SEERS, Cosmic Evolution Early Release Science Survey, led by Prof. Stephen Finkelstein of the University of Texas at Austin, used James Webb's NIR-CAM instrument to look back as far as the epoch of reionization, just after the so-called Dark Ages of cosmic evolution, to study the structure of galaxies in the very early universe. It found more of them than predicted, and they appear bigger and brighter than expected. According to our best models of how the infant universe developed, they aren't supposed to be there so early or look as they do. Some of the first survey results have even indicated there are mature-looking disk galaxies reminiscent of our own Milky Way present as early as 10 billion years ago. We were expecting a more chaotic picture, with predominantly irregular galactic structures interacting violently. James Webb's advanced resolution, coupled with its ability to observe very distant early objects in infrared, has made us think again about how soon galaxies began to form and mature. These findings challenge our current understanding of how the early universe developed and pose some fascinating questions. Were the properties of stars and galaxies in the infant universe dramatically different to now? Might the rate of star formation have been faster and more efficient in the early universe? Could the light from these early objects have been emitted in a way we've never seen before, because the chemical composition of the early universe was different? What does this mean for our best theoretical models of galaxy evolution? Disk galaxies like our own may be where life could develop in the universe, and we're finding them much earlier than we thought. Follow-up observations are ongoing with larger datasets, complementary observations from other telescopes, and spectroscopic analysis from JWST's NIR-SPEC instrument to refine these early results and seek answers to the questions they have provoked. As Christopher Consolis, Professor of Extragalactic Astronomy at the University of Manchester, UK, and a Sears co-investigator said, "Using the Hubble Space Telescope, we thought that disk galaxies were almost non-existent until the universe was about 6 billion years old. But these Webb results push the time these Milky Way-like galaxies form to almost the beginning of the universe." The discovery of unexpected galaxies doesn't end here. Dr. Tim Carlton and a team at Arizona State University have been working on another James Webb Survey-duted pearls, or prime extragalactic areas for reionization and lensing science. As part of this survey, James Webb's NIRCam has picked out an anomalous dwarf galaxy 98 million light-years away, in an area where the team wasn't expecting to see anything. Even more interestingly, its behavior doesn't seem to fit with our current theories of galaxy evolution. Dwarf galaxies are common enough, but this one isn't doing what we might expect. We would expect to see a galaxy like this interacting gravitationally with a bigger companion galaxy nearby, or actively forming new stars, or both. This one, dubbed Pearls DG, is doing neither. It's all alone and its stars are old, challenging our understanding of how galaxies work. It raises the prospect that there could be many more of these anomalous galaxies out there, not doing what we expected, and we haven't been able to detect them until now. In addition, the Webb telescope has also been adding to what we know about the rate of the expansion of the universe. Back in 1929, the American astronomer Edwin Hubble presented the first observational evidence that the universe is expanding in all directions. Hubble proposed the Hubble constant to express the rate of this expansion. Astronomers have known since the 1990s that the rate at which the universe is expanding is increasing, but can't explain why. Explanations to account for this include the mysterious forces known as dark energy or dark matter, but perhaps it's some sort of unknown particle we don't know about yet. Numerous investigations have been undertaken to work out the nature of these unseen components of the universe. Cosmic acceleration can be measured by the distance of objects in the nearby universe and how fast they're moving away from us, or by measuring fluctuations in the cosmic microwave background, heat left over from the Big Bang, linked to the density of matter in the early universe. You'd expect that these two methods would agree with one another, but instead, measurements of the distant early universe suggest a slower rate of expansion than measurements of the nearby, more recent universe. The rate of expansion seems to vary depending on where you measure it. This is called the Hubble tension, and some have gone further and dubbed it the Hubble crisis. We need the Hubble constant to confirm the age of the universe definitively and even predict what might happen in the future. This is a big deal for cosmologists. To put a number on the current expansion rate, we traditionally use measurements of Cepheid variables. These are massive, pulsating stars 100,000 times brighter than our Sun that act as useful distance markers in space. Hubble has been making observations like this in our nearby universe for decades, but there had been speculation that undetected measurement errors might be growing more pronounced as we looked deeper into the universe. Was crowding by other stars and dense dust clouds in the early universe impacting the accuracy of more distant Cepheid luminosity and distance measurements? Maybe this, or something like it, could explain the apparent discrepancy of the Hubble tension. Enter the James Webb Space Telescope and the S80ES team, led by Adam Rees at Johns Hopkins University. Prof. Rice co-won the Nobel Prize for Physics in 2011 for the discovery of cosmic acceleration using data from the Hubble Space Telescope, and he and his team have used James Webb to cross-check the Cepheid variable measurements across the whole distance range of Hubble's observations. With its enhanced precision to pick out Cepheids from other stars and its ability to see through the thick dust clouds obscuring them, James Webb has confirmed definitively that the Hubble photometric observations of the Cepheids are correct. We can now rule out a systematic measurement error. So, what else is causing the Hubble tension? There is the very real and rather thrilling possibility that we need some new physics to explain it. To assist with these new ideas, missions like ESA's Euclid and NASA's Nancy Grace Roman Telescope will conduct wide-field surveys to tell us more about the influence of dark energy on expansion. Roman is due to launch before the end of the decade, with a field of view 100x wider than Hubble. One of its objectives will be to study how the distribution of galaxies and dark matter has changed throughout the history of the universe. Meanwhile, Euclid launched in July 2023 and is already exploring the composition and evolution of the dark universe on a cosmological scale. Like a cosmic version of Google Maps, Euclid will provide astronomers with the most comprehensive three-dimensional inventory of the universe ever. What ESA's Gaia mission, launched in 2013, did for the majority of stars in our Milky Way galaxy, Euclid will do for a huge number of galaxies in the wider universe, precisely determine their position on the sky, their shape, and their distance. How will it do this? Well, a galaxy's distance follows from its so-called redshift. The longer the light from a galaxy has traveled through expanding space to reach our telescopes, the further the light waves are stretched to longer wavelengths, corresponding to a redder color. For the 25 million brightest galaxies observed by Euclid, the redshifts can be directly measured from the spectra obtained by Euclid's near-infrared spectrometer and photometer, or NISP. For 1.5 billion fainter and more distant galaxies, for which no detailed spectra are available, Euclid's near-infrared measurements are combined with at least 4 brightness measurements at various optical wavelengths, obtained by existing large ground-based telescopes such as the Canada-France-Hawaii Telescope, Subaru Telescope, and Pan-STARRS, all in Hawaii, and by the future Vera Rubin Observatory in Chile. From the resulting spectral energy distribution, astronomers can deduce a photometric redshift, albeit less precise than NISP's results. As Euclid's project scientist René Lorais at ESTEC explains, mapping the three-dimensional distribution of galaxies at different redshifts sheds light on the cosmic expansion history. After all, the current large-scale structure of the universe evolved from primordial density perturbations a few 100,000 years after the Big Bang, which have been mapped in detail by ESA's Planck mission. Measuring how the large-scale distribution of galaxies has changed over time will tell astronomers if and how dark energy has also evolved. Of course, to study the role of dark energy in this way, you have to take the existence and spatial distribution of dark matter into account too. That's where the razor-sharp images of Euclid's camera operating at visible wavelengths, also known as VIS instrument, come in. Dark matter doesn't emit any form of radiation, but it betrays its presence by slightly distorting the shapes of background galaxies in a process known as weak gravitational lensing. According to Albert Einstein's general theory of relativity, light is bent by concentrations of mass, whether visible or dark. In other words, a concentration of mass will reveal itself through weak lensing. Thus, a statistical analysis of the shapes of millions of background galaxies at various cosmological distances makes it possible to reconstruct three-dimensional maps of the mass distribution in the universe. In studying weak lensing, the Euclid mission will in fact map local deviations from the average large-scale geometry of the universe, so it's quite appropriate that the mission has been named after Euclid of Alexandria, the father of geometry, who lived in the 3rd century BC. In addition to mapping the distribution of dark matter and revealing the expansion history of the universe, Euclid will also measure a parameter known as gamma, which describes the growth of structures like clusters of galaxies. If this parameter doesn't match predictions from general relativity, that would support alternative theories of gravity, like MOND, for modified Newtonian dynamics. With MOND, you pretty much get what's on the label. At planetary or solar system scales, Newton's gravity works just fine, of course, except where you need the more detailed calculations of gravity provided by general relativity. But once you go big, the usual F equals ma we're familiar with doesn't quite apply, and the relationship between force and acceleration follows a different rule. Under MOND, there's no need for an additional particle to explain the observations, just a slight tweaking of the gravitational force. And because the tweaking of gravity under MOND is explicitly designed to explain the motions of stars within galaxies, it naturally does that very well. The theory also doesn't suffer from the overproduction of satellites and the extremely high galactic cores of dark matter. But MOND is far from perfect. The modifications made to gravity to explain stellar motions have trouble explaining the motions of galaxies within clusters and the lensing of background light. And MOND isn't a fully relativistic theory. All modern theories of physics must be compatible with special relativity. An update to MOND that is equivalent, called TVES, can compete head-to-head with general relativity and falls far short. Models based on modified gravity have significant trouble explaining the growth of structure in the universe, features of the cosmic microwave background, and more, all places where dark matter works quite well. There is no MOND-like theory that can account for every single observation when it comes to dark matter. All of them fail at least one test. While MOND may still be accurate when it comes to galaxy rotation curves, there are enough observations to tell us that we would still need dark matter to exist in the universe. No, the dark matter hypothesis isn't perfect, but then again, no scientific hypothesis is. When evaluating competing hypotheses, scientists can't just go with their guts or pick one that sounds cooler or seems simpler. We have to follow the evidence, wherever it leads. What's notable, scientists working on CERN's Compact Muon Solenoid (CMS) experiment have published the latest data in their search for a long-lived exotic particle known as the dark photon. Dark photons, also called hidden photons, differ from regular photons, particles of light, in that they are thought to have mass, making them a prime candidate to explain dark matter. Dark matter, as told, is the catch-all term to describe seemingly invisible stuff in space that has only been observed via its gravitational effects. But it has never been directly detected, and no one is sure what it actually is. Physicists at CMS are trying to change that. Like particles produced in other experiments at CERN, the hypothetical dark photons would be produced by the decay of another particle, the Higgs boson, which was proposed in the 1960s and famously observed in 2012. Higgs bosons are thought to decay into dark photons, which then would decay into displaced muons. The CMS collaboration is working to constrain the parameters at which that process would occur. CERN's Large Hadron Collider began its third run in July 2022, with a greater capacity for particle collisions than in its previous runs. This means that the CMS experiment's algorithm, or trigger, which detects interesting collisions, has more events to sift through, and thus more opportunities to spot displaced muons that resulted from dark photons. Dark photons are considered long-lived by particle standards. They exist for 1/10 of a billionth of a second. Despite their longevity, they are difficult to spot, which is why no one has done so yet. In fact, the search for dark photons has been going on for years. As physicist James Beecham said, dark photon searches are simultaneously straightforward and challenging. Straightforward because the concept is general and simple enough that designing experimental searches is pretty easy, but challenging because we really have no clue where in the parameter space the dark photon could live. Some scientists are looking for dark matter using little mirrors, while others are trying to tune into its frequency with a dark matter radio. At CMS, physicists are trying to spot the particles as they decay into muon pairs. In a boost for CMS, the Large Hadron Collider will soon be upgraded. The Large Hadron Collider at CERN now is capable of reaching energies of approximately 7 TeV per particle. That equates to accelerating protons to 299,792,455 menorS apiece, just 3 ms shy of the maximum achievable speed in the universe, the speed of light. At this speed, they circle the ring about 11,000 times per second. If they were traveling around the equator, instead, they would circle the Earth 7.5 times per second. These beams are then made to collide inside several large detectors, the largest of which is as tall as a 7-story building. The collisions are incredible. They occur about 1 billion times per second and generate very hot temperatures, about 100,000 times hotter than the center of the sun, or 10 times hotter than the center of a supernova, which is the explosion of a star so violent that it can be seen billions of light years away by modern telescopes. Though this sounds scary, each collision actually occurs at a very small scale, smaller than the size of an atom. That's why the equipment doesn't get damaged. But if we want to understand the universe of particles better than we understand them today, are to probe the universe at higher energies and/or at greater precisions, with more collisions than ever before. It's possible to go to higher energies, but the only ways to achieve them are to either increase the physical size of the accelerator, which realistically requires building a new accelerator, or to increase the strength of your bending magnets. It's historically been considered worth it to build a new accelerator when you can increase your energy by a factor of 7 to 10 or more, which is the energy leap that was made from Fermilab's Tevatron to CERN's LHC, and which is the planned leap from the current LHC to the proposed Future Circular Collider, or FCC, the leading prospect for humanity's next particle collider. It's important to plan for that, but also to recognize that it will take more than a decade to construct it. In the meantime, however, the LHC just completed a major part of an enormous upgrade to what's being called the HL-LHC, or High Luminosity LHC. In astrophysics, luminosity refers to how bright an astrophysical source is. In particle physics, it's how luminous, or rich in particles, the beam is. By creating more bunches of particles that collide more frequently, and by increasing the number of particles that collide when two bunches cross each other, the current incarnation of the LHC has already broken the all-time luminosity record for particle colliders. In fact, over the next 10 to 15 years, the LHC will take somewhere between 40 and 50 times as much data as it's cumulatively taken so far, since its first turn-on in 2008. In other words, the LHC data we've collected and analyzed so far represents only about 2% of the total data that the LHC will wind up accumulating. The LHC measures the total amount of collected data in what we call inverse femtobarns, and had collected 150 inverse femtobarns by the close of operations in 2018. The HL-LHC will collect over 250 inverse femtobarns each year when it's complete. With that data, the LHC will be able to test the standard model in an unprecedented series of ways. They'll be able to create greater numbers of Higgs bosons than ever before, testing whether it decays according to the standard model's predictions to better than Barrier 1 part in 100 precision. They'll be able to test lepton flavor universality, currently one of the 3 still-standing standard model anomalies, along with the W boson's mass and the muon's anomalous magnetic moment, to unprecedented precision. If it's a real problem with the standard model, this will undoubtedly push it over the gold standard 5 sigma threshold. They'll be able to test whether the CDF collaboration's measurement for the W boson's mass matches their value, with much more, albeit less clean data, than Fermilab was ever able to collect. They'll be able to test top quark and bottom quark physics to better precision than ever, either confirming the standard model's predictions or running counter to it. And, perhaps most excitingly, they'll look for clues of new physics in places where we might not expect it. With nearly 98% of the total data that the LHC will eventually take left to go, giving up on the possibility that it will find something worth writing home about is both unnecessarily defeatist and also wildly premature. Sure, the expectations of theorists for what might lie beyond the standard model have turned out to be abysmal, as all of the scenarios preferred by the community are sorely lacking in any substantial evidence. But the failure of a detective to imagine what clues ought to be there is no excuse for giving up on the case. Yes, it's arguable that theorists have been doing nothing more than stabbing in the dark, and appear to have missed thus far with each and every strike. Yes, the LHC hasn't found a new fundamental particle beyond the standard model yet, and it's plausible that it may not, even once 100% of the data has been taken. And yes, there are a number of cracks in the standard model, and modern particle physics cannot account for a wide variety of observations concerning our universe. But the successes of particle physics cannot be ignored, and that's a remarkable triumph of the standard model where all of its alternatives fail. In the quest for the next big breakthrough concerning the nature of reality, there's no reason to expect that the fruit we seek will be on the lowest hanging branches. But if we fail to climb the tree of knowledge and see what we discover all the way along our journey to the top, we'll have only ourselves to fault. The game is not yet over, but we can be certain that the surefire losing move is not to play at all.
It's so powerful, it might have just shattered our understanding of the universe.
Out in the depths of space, the James Webb Space Telescope is living up to its hype. From inexplicably bright galaxies to life on alien planets, and even the potential demise of our standard model of the universe, the most powerful telescope ever built has blown our minds with its stunning discoveries of multiple structures that shouldn't exist.
That's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us as we dig deep into how the shocking discoveries of James Webb could destroy the universe. To understand the dilemma, let's start by taking a quick look at the Big Bang, our best supported theory of our universe's origin. Originally, the Big Bang was a simple idea that grew out of three facts, all put together. In Einstein's general theory of relativity, a universe filled with any uniform distribution of matter and/or energy will not be stable in a static configuration. The fabric of space in that universe must either contract or expand. Observationally, there are spirals and ellipticals in the sky, and they lie well beyond the Milky Way. Their distances can be measured. Also, observationally, the light from these spirals and ellipticals appears to be shifted, with more distant objects exhibiting a greater redshift in direct proportion to their distance, consistent with an expanding universe. By combining these three facts, we'd conclude that the universe, if it's expanding and becoming less dense today, must have been smaller and denser in the past. The first person to synthesize this information together was Georges Lemaitre, who did it in 1927, although others would independently come to the same conclusion, including Howard Robertson in 1928, Edwin Hubble in 1929, and Arthur Walker a few years later. Over time, we were able to derive many more consequences from the Big Bang, including that the early state must have been hotter as well as denser, and that as the universe expands, it also cools. This allowed us to predict that there would be a leftover bath of low-energy radiation, with a blackbody spectrum in all directions, arising from when the universe cooled through the threshold that enabled it to form neutral atoms. At even earlier times been hot and dense enough to initiate nuclear fusion reactions before any stars could form. leaving us with an initial abundance of elements other than hydrogen among the pristine set the universe begins with. And that, once neutral atoms form, the universe begins gravitating to form structure in the universe. Stars, star clusters, clouds of gas, galaxies, galaxy clusters, and eventually the great cosmic web, filled with filaments and voids. All of these aspects of the Big Bang have been verified and validated, ruling out a great many alternatives that cannot reproduce these successes. Today, there are 3 additional ingredients that we've learned, and tested and verified, are also present in the universe. Dark matter, which clumps and gravitates but doesn't collide with normal matter or photons. Dark energy, which behaves as a form of energy inherent to space itself. And cosmic inflation, which limits how far back into the past we can extrapolate the hot Big Bang before matter and radiation no longer dominated the energy contents of the universe. This picture enables us to do something remarkable. Inflation allows us to describe the initial conditions of the universe at the start of the hot Big Bang, how hot and dense it was, what the initial spectrum of density imperfections were, including that we're all adiabatic, Gaussian random fluctuations, and what the magnitude of these fluctuations were on all cosmic scales. Our knowledge of the Standard Model, plus the additions of dark matter and dark energy, enable us to state what the various types, energies, and abundances of all the different species of energy were at all cosmic times. From that starting point, our knowledge of the laws and interactions that govern the universe enables us to time-evolve these initial conditions from the start of the hot Big Bang all the way up through the present day. We can make both theoretical predictions and perform numerical simulations that tell us what should arise and when in an expanding universe that begins with a hot Big Bang and the properties we've determined it ought to have. However, despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. And with the recent addition of the James Webb Space Telescope to the arsenal of tools astronomers have, James Webb continues to fuel doubts about the Big Bang theory, as its early universe observations cannot be explained by current cosmological models. The James Webb has literally gone further than any similar instruments used by NASA before. As Matt Greenhouse, who has served on the James Webb's senior staff as a project scientist, the James Webb Space Telescope has given humanity its first high-definition view of the infrared universe. Thanks to Webb's unprecedented capabilities, for the first time, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Prior to James Webb, we had one confirmed galaxy, GNZ11, at an age of about 400 million years after the Big Bang, and only one other galaxy candidate, possibly at an age of around 330 million years after the Big Bang. No other stellar or galactic signals from such early epochs had ever been seen. Fast forward to the present day, more than 2 years after James Webb began science operations, and the story has changed dramatically. We have over 100 galaxy candidates from James Webb that take us back to the first 300 million years of the universe, and several of them have already been confirmed to indeed be ultra-early and ultra-distant. GNZ11 is now only the 11th most distant galaxy known. All 10 of the top 10 most distant objects were discovered and measured with James Webb. However, what's notable is that many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. For example, they appear to be very massive, very bright, very rich in heavy elements, very actively forming new stars, and very rich in gas. The fact that we see so many galaxies with these properties so early on is puzzling, because we believe we understand how gas infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, And although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Therefore, when we look at these very early galaxies, we do get the impression that something is amiss. Webb's finding then caused a stir in the astronomical world, with some scientists suggesting that it had put our current view of galaxy evolution, or even our understanding of the universe, into doubt. There weren't just inexplicably large ancient galaxies on James Webb's list of discoveries, but whopping black holes, too. The first, Sears 1019, had a mass 10 million times that of our Sun and was found by the James Webb Telescope just 570 million years after the Big Bang, making it the oldest black hole ever spotted at the time of its discovery in April 2023. We say at the time, because James Webb didn't rest on its laurels. Earlier this year, the telescope broke its own record again for the most distant black hole ever seen to date. The black hole dwells in the ancient galaxy GNZ11, which is 13.4 billion light-years away and is thus seen as it was just 400 million years after the Big Bang. The black hole itself is around 6 million times as massive as the Sun and seems to be feeding on matter from its surrounding galaxy 5 times more rapidly than the limit suggested is sustainable by current theories. And according to scientists, this discovery could be a giant step forward for black hole science, especially in understanding how supermassive black holes reached masses equivalent to millions of billions of times that of the Sun in the very early epochs of the universe. For decades, how these gigantic space-time ruptures swelled to such staggering scales so early on is an ongoing mystery. Astrophysicists are currently exploring options that include the black holes being formed from the rapid collapse of giant gas clouds, although they haven't ruled out that some may have been seeded by hypothesized primordial black holes, thought to be created moments after, and in some theories even before, the universe began. In another stunning observation, the James Webb Space Telescope has found more thousands of Milky Way lookalikes that shouldn't exist, swarming across the early universe. Shaped like warped vinyls and sporting delicate spiral arms, the Milky Way doppelgangers were found by James Webb more than 10 billion years into the universe's past, during a period when violent galactic mergers were thought to have made an abundance of such fragile galaxies impossible. But Webb's finding revealed that the disk galaxies are 10 times more common in the early universe than astronomers previously thought. The strange discovery joins others made by James Webb that point to a deepening mystery around how large galaxies, and with them the potential for life, first bloomed in our universe. However, not stopped there, Webb's ultra-powerful eye has also revealed glimpses of completely new, unexplainable objects. After being trained on the Orion Nebula, the Webb telescope found 42 pairs of Jupiter-mass binary objects, or jumbios, Jupiter-sized planets drifting through space in pairs, some as far apart from each other as 390 times the distance between Earth and the Sun. The jumbos are too small to be stars, but as they bafflingly exist in pairs, they are unlikely to be rogue planets ejected from solar systems. Their discovery has alerted astronomers to a brand new formation mechanism for planets or even for failed stars. While James Webb glimpsed deep space unlike ever before, it caused a stir in the whole scientific community as piercing through dust to find an ancient ghost. Look at this picture. It's a very blurry, highly dust-obscured resident of the cosmos, whose name is only a string of numbers and letters. It even sits at a distance so far from Earth that it slips in and out of the watchful eyes of various telescopes. The image, captured by the powerful James Webb Space Telescope, spotlights galaxy as TECC 71. But what's striking here is that we're seeing as TECC 71 the way it was just 900 million years after the Big Bang. That's when the universe was turning on its very first stars, absolute eons before our solar system was born. The Webb's view of this galaxy as a hazy speck of light is a far cry from many other glorious images of galaxies and galaxy clusters in its repertoire. However, even this smudge holds important lessons for our understanding of the early universe. Elsewhere, James Webb has helped set yet another record. Using the James Webb Space Telescope, astronomers have discovered star clusters in the cosmic gems arc that existed just 460 million years after the Big Bang. This marks the first discovery of star clusters in an infant galaxy, seen as it was when the 13.8 billion-year-old universe was less than 500 million years old. The cosmic gems arc, initially discovered by the Hubble Space Telescope and officially designated SPT-0615JD1, is a gravitationally lensed infant galaxy around 13.3 billion light-years from Earth. That means light from this galaxy, seen by James Webb, has been traveling to Earth for around 97% of the universe's lifetime. The international team of astronomers behind this discovery found 5 young, massive star clusters in the cosmic gems arc. These clusters existed during a period when young galaxies were undergoing intense bursts of star formation and emitting huge amounts of ultraviolet light. This radiation may be responsible for triggering one of 2 major phases in the evolution of the universe, the epoch of cosmic reionization. And when pointing Webb's sights on a star cluster about 1,000 light-years from Earth, astronomers discovered some unusual objects that is likely to be the least massive, free-floating brown dwarf that has been observed to date. In another remarkable observation, James Webb spotted a massive, gassy tendril composed of 10 closely packed galaxies stretching over 3 million light-years. According to the researchers, this ancient filament of gas and stars may represent the oldest known thread of the cosmic web. Another addition to the Webb telescope's long list of cosmic distance records was its discovery of the most distant gravitationally lensed object ever seen, an Einstein ring, produced by the warping of light from a distant galaxy around a mysteriously dense foreground galaxy. How distant? A mind-bending 21 billion light-years away, which, given the universe's 13.8 billion years of age, means that the light from the galaxy traveled almost twice that distance due to the cosmos's expansion. Besides making for a very pretty picture, distantly lensed light shows like this could help astronomers to understand the puzzling nature of dark matter, the unseen substance believed to make up 70% of the universe's matter. Notably, while focusing to unlock the secrets of deep space, the James Webb Space Telescope also is revolutionizing our understanding of our closest cosmic neighbors. With its powerful infrared instruments, sharp spatial resolution, and exquisite sensitivity, Webb is forever changing our view of our celestial backyard. It is helping scientists answer important questions about our solar system, including how was the solar system formed and how has it changed over time? Where did the chemicals necessary for life on Earth, like water and carbon compounds, come from? What are the icy small bodies in the outer solar system made of? How are planets around other stars like planets in our solar system? Webb's extraordinarily sensitive spectroscopic instruments and state-of-the-art imaging capabilities enable analysis and mapping of solar system objects' atmospheres and surfaces. This is critical for studying planets, dwarf planets, moons, comets, asteroids, and ring systems. However, because Webb cannot point toward the Sun, it cannot observe objects between it and the Sun such as Mercury, Venus, Earth, or Earth's moon. Despite these challenges, exciting early results prove that it is possible to study planets with Webb. The telescope captured images and spectra of Mars, which allow scientists to study short-term phenomena like dust storms, weather patterns, seasonal changes, and, in a single observation, processes that occur at different times during a Martian day. In addition to finding the speedy Jovian jet stream described, Webb's view of Jupiter includes many fascinating details, including auroras, hazes, and tiny moons. In addition to finding carbon on the surface of Jupiter's moon Europa that likely originated in its subsurface ocean. In the newest study, astronomers have used James Webb to find previously unseen structures and activity in Jupiter's atmosphere, above the Great Red Spot. These odd features seem to be caused by powerful atmospheric gravity waves. The Great Red Spot is the largest storm in the solar system, twice as big as Earth, and is believed to have been raging for at least 300 years. The winds of the Great Red Spot rage at around 430 to 680 kilometers per hour, up to 3.5 times as fast as a tornado here on Earth. But, despite the storm's age, size, and power, scientists had actually suspected that the atmosphere of Jupiter above the Great Red Spot wasn't all that interesting. However, these new observations delivered by James Webb's NIR-SPEC instrument, which observed the massive scarlet storm in July 2022, show that this assumption couldn't have been more wrong. After all, Jupiter never ceases to surprise. The telescope also detected a shockingly large water vapor plume spewing from Saturn's moon Enceladus. For the first time, Webb is giving scientists a direct look at how the water gushing from the surface of Enceladus, first detected by the Cassini spacecraft, feeds the entire system of Saturn, including its rings. Using Webb's infrared vision to study the atmosphere of Saturn's moon Titan, the only moon in the solar system with a dense atmosphere, scientists detected clouds and observed airflow. For those who don't know, Titan is the only planetary body other than Earth that currently has rivers, lakes, and seas. However, unlike Earth, the liquid on Titan's surface is composed of hydrocarbons, including methane and ethane, not water. Put Titan aside, Webb's huge mirror and infrared sensitivity make it easier to see small, faint bodies such as Kuiper Belt objects, comets, asteroids, and centaurs. In the first demonstration of this capability, described in detail above, Webb captured the DART impact, NASA's inaugural attempt to move an asteroid in space. Webb enabled another long-sought scientific breakthrough, this time for solar system scientists studying the origins of Earth's abundant water. Using Webb's NIR-SPEC, or near-infrared spectrograph instrument, astronomers for the first time have confirmed gas, specifically water vapor, around a comet in the main asteroid belt. This indicates that water ice from the primordial solar system can be preserved in that region. However, the successful detection of water comes with a new puzzle. Unlike other comets, Comet 238P Reid had no detectable carbon dioxide. Scientists also used Webb to capture the shadows of starlight cast by the thin rings of Chariklo, a small icy body more than 2 billion miles beyond the orbit of Saturn. Only 250 kilometers, or 1,051 times smaller than Earth in diameter, Chariklo is the largest of the known centaur population. Its rings orbit at a distance of about 400 kilometers from its center. Information gathered from these rings will allow astronomers to explore the ring's thickness, the sizes and colors of the ring particles, and more. Scientists hope to gain insight into why this small body even has rings at all, and perhaps detect new, fainter rings. Besides, remember that many different kinds of ice exist in the outer solar system, not just the familiar water ice. Other molecules besides water can form ices, such as nitrogen, methane, ammonia, and carbon dioxide. Webb excels in the study of ices in the solar system through the use of spectroscopy. Most often, it provides reflectance spectra, sunlight shining on an object and reflecting back, while the surface absorbs particular wavelengths of light. For ices in the outer solar system, it's not just the composition that matters, it's also the shape and structure. Different structures of ice, such as amorphous, crystalline, and irradiated, look different in spectra. The type can tell scientists about the temperature history of the object. In crystalline ice, the molecules are arranged in a highly regular pattern, forming lattices, such as in typical water ice on Earth. With amorphous ice, the molecules are irregularly grouped. In the cold, primordial gas between stars and across the universe, amorphous ice is the most common form. This is why Webb's integral field units are especially important. With a spectrum in every pixel, scientists can map out the surface of an object. One good example is Jupiter's moon Europa. By looking at a map of the carbon dioxide on Europa, we can tell that the carbon originated in the oceans because it is most abundant in a region where the terrain is quite new. Another example of the exquisite quality of Webb spectroscopy is the clear signature of crystalline ice revealed for the first time on Chariklo. Ground-based telescopes had hinted at this ice, but Webb saw the crystalline ice signature for the first time. Some of Webb's most intriguing discoveries involve searching for the building blocks of life beyond Earth. This search hinges on the accurate identification of chemical markers, such as water, carbon dioxide, and ammonia. These markers have strong infrared signatures that Webb can detect in the atmospheres and on the surfaces of planets, moons, and smaller bodies. And in a remarkable finding, James Webb has spotted the potential signs of life in alien farts on a Goldilocks water world 120 light-years away. The exoplanet it found, K2-18b, is a sub-Neptune planet, weighing in somewhere between the mass of Earth and Neptune, orbiting the habitable zone of a red dwarf star. After taking an atmospheric spectrum, the Supreme Space Observatory found it rich with hydrogen, methane, and carbon dioxide, all chemical markers of a hydrogen-rich Hycean world that is a prime contender for extraterrestrial life. More tantalizing still was the detection of dimethyl sulfide, a cabbage-smelling compound only known to be produced by microscopic algae in Earth's oceans. The researchers want to take more peeks at K2-18b and worlds like it to find further evidence for extraterrestrial life beyond our planet. Fascinatingly, the latest result of James Webb suggests an exoplanet is our best bet at finding an alien ocean. Dubbed LHS 1140b, the exoplanet orbits a red dwarf star about a fifth the size of the Sun and sits 48 light-years away from Earth in the constellation Cetus, which, as luck would have it, translates to the whale. But the most important about LHS 1140b is the fact that it lives in its star's habitable zone, otherwise known as its Goldilocks zone. As that nickname would suggest, this is the area around a star where it's neither too hot nor too cold for a world to host liquid water, but rather fits the standard by which the fairy tale character Goldilocks lives. There's also a second major win for the world. Though it has been making headlines now due to the new study involving Webb's data, LHS 1140b has actually been on planetary hunters' radars for some time. In fact, experts had already theorized that this could be a water world in the past, and even shared similar sentiments about how it could offer humanity the first ever direct evidence of exoplanetary liquid water. None of that is new. Scientists themselves have touted the world's promise previously, and an army of telescopes has investigated it in solid detail, including the now-retired Spitzer telescope, the Hubble Space Telescope, and the Transiting Exoplanet Survey Satellite, or TESS for short. However, there was something missing until now: the James Webb Space Telescope's keen eye. It was necessary because, for a long time, there was something like a gap in the literature about LHS 1140b. Basically, the trouble was that scientists couldn't quite confirm whether the exoplanet is a mini-Neptune, a planet less massive than our original Neptune, but one that still has Neptunian characteristics, or a super-Earth. A super-Earth is a world that's larger than Earth, but still either rocky or water-rich. The latter typically sounds the potential habitability alarm, and James Webb, scientists had imagined, could be the one to set it off. This appears to have been an accurate inference. As the team's statement on the study suggests, their work not only strongly excluded the mini-Neptune scenario, but also confirmed the world may have a nitrogen-laced atmosphere like Earth does. It is certainly worth noting that LHS 1140b isn't exactly fully alone in its exhilarating characteristics. There are also a variety of other habitable zone exoplanets scientists are drawn to. The most obvious are probably the 7 worlds of the TRAPPIST-1 system, a planetary lineup that looks almost disturbingly similar to our solar system structure. The septet of orbs resembles our octet, and some of them are in the habitable zone like Earth is. However, a very interesting Webb study actually complicated the search for habitability in TRAPPIST-1 quite recently. It revealed that the system's anchor star is incredibly active in such a way that it could skew our observations, making us believe a world in the system is habitable when it really isn't. Even James Webb has its limitations. So, to that end, LHS 1140b does have a few special embellishments. For example, data obtained by James Webb further suggests the exoplanet's mass might be made of between 10% and 20% liquid water. And it paints a fantastical picture of what the planet might look like in simple terms. It could look like a snowball, essentially, that orbits its star while rotating in such a way that one side always faces that star. It's kind of like the moon's orbit around Earth. We can't ever see the far side of the moon because the moon rotates at the same rate it revolves around Earth. One side never faces us, and the other always does. Similarly, this would mean that if James Webb's illustration of the LHS 1140b scene is correct, the side of the planet always facing its sun would be exposed to lots of heat. This would be the part of the snowball that's melted into a liquid ocean. And yes, if so, LHS 1140b has an Earth-like atmosphere, and its surface temperature of the ocean may very well even be a comfortable 20 degrees Celsius. And that is a very promising start. A previous study, the Webb telescope, revealed details of the mysterious gas giant exoplanet WASP-39b, which orbits a star about 700 light-years away from Earth. WASP-39b is tidally locked to that star, which means the same side of the planet always faces its star. In other words, half of the planet experiences perpetual day, and the other experiences perpetual night. But the dividing line isn't black and white. There's a proverbial gray area between the two halves that experience the equivalent of eternal dawn and eternal twilight, and it's in these areas that James Webb is revealing new information. Using those data, astronomers determined the temperature difference between these two transitional areas of the planet, a whopping 200 degrees Celsius. The morning is cooler at 600 degrees Celsius, while the evening is warmer at 800 degrees Celsius. What's more, models based on Webb's data also revealed weather patterns in these regions. For one thing, the dawn side is cloudier than the evening side. For another, the prevailing winds on WASP-39b appear to move from the night side to the morning, to the day side, then to the evening, at speeds up to thousands of miles per hour. Astronomers will continue to dive into this data set to learn more about WASP-39b and other exoplanets. In addition, James Webb has mostly revealed insight into how everything began, but what about our eventual demise? Fear not, or maybe fear away, doom mongers. The James Webb telescope had you covered this year with a spectacular light show from a dying star, a preview into the demise of our solar system. The donut-shaped ring nebula, also known as Messier 57 or M57, is a 2,200 light-years distant corpse of an exploded star, harboring at its center a tiny pinprick of a white dwarf that is the last remaining piece of the star's core. As it reached the end of its life, the star exploded outwards, hurling its innards far and wide to form what looks like a gigantic eye. The explosion likely obliterated or ejected any unfortunate planets in its way, a fate that will similarly befall our own solar system in 5 billion years' time. One of Webb's recent observations has found evidence of two giant asteroids slamming into each other in a nearby star system. The colossal collision ejected 100,000 times more dust than the impact that killed the dinosaurs. The violent impact occurred recently in Beta Pictoris, a star system located 63 light-years away in the constellation Pictoris. While the young star system currently contains at least 2 gas giant planets, it has no known rocky worlds like our own. But rocky inner planets may be in the process of forming thanks to large dust-producing collisions like the one spotted by James Webb, the researchers behind the new findings said in a presentation at the 244th meeting of the American Astronomical Society in Madison, Wisconsin. Because it is still very young, the star system's circumstellar debris disk, the vast ring of gas and dust surrounding the star, is a significantly more violent place than our own, making it the perfect place for astronomers to study the tumultuous early years of planet-forming systems. The team added that their findings could offer a rare insight into the history of our own solar system. And when it comes to hunting for the explosive deaths of massive stars in the early universe, James Webb is quite the cosmic detective. This celestial Sherlock Holmes has found evidence of 80 new early supernovas in a patch of sky as wide as a grain of rice held at arm's length. Not only is this 10 times more supernovas than have been uncovered before in such early cosmic history, but the sample also includes the earliest and furthest supernova ever seen. It's one that exploded when the 13.8 billion-year-old universe was just 1.8 billion years old. Data from the James Webb Space Telescope Advanced Deep Extragalactic Survey, or JADES program, helped a team of scientists find this unprecedented clutch of supernovas, which further includes Type 1a blasts that astronomers call standard candles and can use to measure cosmic distances. Prior to James Webb's commencing operations in the summer of 2022, only a handful of supernovas had been found dating back to when the universe was only 3.3 billion years old, equal to around 25% its current age. However, the JADES sample contains many supernovas that exploded even further back in the past. In fact, some erupted when the universe was less than 2 billion years old. On the other hand, it is worth noting that while the James Webb's primary goal is to produce awesome science, and not just pretty pictures, sometimes the pretty pictures are the awesome science. Case in point, the stunning portrait of NGC 5068, a spiral galaxy sitting about 17 million light-years away. No ordinary galaxy, this one is spouting off new stars at a record pace. A team of astronomers was able to use multiple instruments on board the telescope to capture the galaxy in all its glory. After all, James Webb has beat all our expectations. What's more, the telescope is just taking its first steps into its journey to conquer the universe. Space engineers have calculated Webb's expected 10-year lifetime could be doubled. In many ways, that is very good news. We will be able to do a lot more science with it now. In the next years, the telescope promises to deliver images of staggering beauty, while also providing scientists with data that has revolutionized our understanding of the cosmos. And that's really worth waiting. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.